the spin projection.
Like the basis sets for the spin projections.
They're the matrix representation of the operators for projection of spin in a z basis. Right? Right? Well, then you got to multiply them all by h bar over 2. So without the h bar over 2.
Now why does the y one have i's instead of ones?
Well, because the I is again a phase, all right. But right now, what it means is that well, these are all Hermitian still, right?
Yeah.
Yep.
So you can get real observable. So the I that appears in these things always has to do with the phase. So what it's going to mean is,
So because it's got an XY projection, so one of them has to be like the e to the I theta
And one will be
angular
rotation, yeah.
in that 2D plane.
yeah.
Gotcha.
So what it means is that you can to construct. Well, we're going to do an example of it, but we're going to, in order to construct, for example, a ket for the spin in the x or the y direction. It is not going to just be one thing. It's going to be a linear combination of the spins in the z direction, and it's possible that that linear combination of the spins can have a phase angle. Okay? Okay, so what we're going to have to do is we're going to have to build this, all right? So let's do it. That's the next question. But let's before we do anything, let's do a quick check, all right? Let's do a check. And let's do like an SZ on a up in the z. All right, and that equals h bar over 2, 1, 0, 0, 1, and then an up in the z is 1, 0, and so that equals h bar over 2. This is 1 plus this
0.
0. All right. So what do we say? So this is h bar over 2 over 0, which equals h bar over 2 times 1, 0. Right? And that equals h bar over 2 times an up into z. Right? So did this explicit representation of the projection of angular moment of projection in the z direction work?
Yes.
Did that work explicitly? So yes, it did. I mean, this is the explicit.
Is that S sub z and z basis?
Yeah. So
Just get
everything's
lost
on
in
the z
the
basis.
detail.
Check on
All
the z
right.
basis.
So what does that say?
That's actual z direction.
Well, what it's saying is that if the projection of angular momentum in the z direction acting on the state gives me h bar over 2.
Oh, apart.
Right?
Apart.
Yeah.
And so does that all get added on to the rest of the psi n stuff?
Yeah.
So it's like psi n's this, we figure all that stuff. We
Yeah.
don't figure out spin for that too.
Yeah. Most definitely. Yeah, I mean, Mike's point is interesting. What we're trying to do is we're trying to build a hydrogen atom. Right? And at the moment, psi n equals e to the minus I, and then it's going to be minus 13.6 EV over n squared, over h bar times t, all right, times NL ML, right?
That's
And now at that end, we can tack on, if you want, an S and an MS. Or on the end, you could tack on a spin particle that can be up or down, something like that.
That's just multiplying.
And that's a big size?
Yeah. This would be the big side, yeah.
So that would be just multiplied by another term. Since there's another term multiplied into it.
What's that?
It's a multiplying factor.
Yeah. Because it's independent. So if you wanted, guys, let's back up even further. Let's pretend that you had the spin. It's kind of like if you assume the separation of variables, you separated out the spin part, with all the other parts. And now you're just gonna multiply it all together as a result of separation of variables.
Because you've got two negatives in the exponent of e, you just got rid of the negative.
Well, that's what I was looking at. I'm not sure that that makes sense, but the energy
Negative
is...
I times negative 13.6 eV gives you, if you have the negatives.
Yeah, so it becomes positive, and I'm not sure as I was writing that down, but it's an oscillatory term. It's not a positive exponential. It's not a number. It's still an oscillatory term. Yeah.
Is it legal to write that though? I thought that was disallowed.
What do you mean?
Write cat.
It's what I would do in general is I would say, here's how I would do it. You know, you can do it any way you want. It's your own abstraction here, all right? But here's how it might be written more appropriately.
Yeah, just all in one.
Yeah, all in one. And so we're just going to keep, so remember, we got a quantum number for essentially every degree of freedom that we had. So when we had spherical a problem in 3 dimensions, we had 3 quantum numbers. And so now if you want to look at it, the spin lives in a whole brand new space. So now we're talking about this abstract 4-dimensional space, 3, x, y, and z.
Yeah.
And now we have this abstraction into a spin space.
R and phi theta, and then the spin.
R phi theta, R phi phi is 3,
Yeah.
and then spin
Extra.
is an extra dimension. Yeah.
In the general notation with the SMS at the end, how would you know if it's the spin up or the spin down? Just reusing, would you?
So
Could
here's
you
how
write
you write it.
S
So
plus?
for example, let's look at
X bar
this.
over 2 and then up or down.
Let's look at this. Here we go. So let's look at n equals 1. All right? So it's a 1, 0, 0.
Right.
Everybody agree?
Yep.
N, L, M, L.
Yep.
Yeah.
Let's make it a spin down. So it's going to be 1/2, because its spin is 1/2,
Right.
right? Just like, remember, y to the LML, the spherical harmonic gave us what the angular momentum is, right? But then what is ML? It's the projection of the angular momentum. So here, what is the spin of this particle?
Negative h bar.
No.
It's still negative 1/2.
No.
The spin is always going to be 1/2.
The spin is 1/2. What is the projection of the spin?
Negative 1/2.
Minus 1/2. That's the distinction I'm trying to make.
So it's either going to be, at the end, you're always going to have a 1/2.
So what's the spin of a spin half particle that's up?
1/2, 1/2.
What is the spin of a particle, 1/2 particle that's down?
Minus
1/2. What's the projection of a spin half particle up? 1/2. Right? What's the projection of spin of a particle down? Minus 1/2.
So you could replace the SMS with 1/2 plus or minus 1/2?
Yeah, you know, if it's not determined right there. And so what is this big thing? It's a ket. What is a ket? It's a complex abstract vector space representation of our solution. Right? I mean, that's what we're trying to get to. Yeah? So we're just going the next step. Now, I will tell you that when you use the Dirac equation, it gets a lot messier because you can't, the spin comes out of the relativistic Hamiltonian. So the solution spin is automatically in there. And it doesn't appear as this nice thing that you can tack on at the end.
Built in,
What's that?
built in.
So when you, so here's the scoop, is that when you solve Schrödinger's equation for the Dirac equation, when you solve the Dirac equation, which is the relativistic Hamiltonian, the solutions automatically include the Pauli spin matrices.
So you have to factor them out.
Well, I mean, let's just talk about this in general. So when you solve Schrödinger's equation, right, you get one answer for psi.
Well, when you solve the...
And you tack this on at the end.
Well, with the relativistic...
When you write down the Dirac equation, you can't get a solution, just one solution. You automatically have 4 solutions. Right? And those 4 solutions correspond to an electron spin up, an electron spin down, and then a positron spin up and a positron spin down. So there is no one-dimensional solution to the Dirac equation. It doesn't exist. It comes in 4. So in other words, as soon as you write down a relativistic Hamiltonian, you're just saying that nature has to have spin, which is pretty profound, I think.
Mm.
And when you,
Hybrid
when
actually.
you calculate that with that equation, you deal with like individual particles.
Oh, yeah, yeah.
There's no, like, I can't imagine a way to do this with like groups of particles, even like a handful.
Well, yeah, I mean, here's what it comes down to. Let me see if I can draw. This is kind of what Dale and I are kind of working on right now, and this is what you do in particles. So the Dirac equation, so E total equals the square root of C squared P squared plus M0 squared C to the 4th, right? And so Schrodinger's equation is H psi equals IH partial psi with respect to T. And so remember, you know, the square root in the Hamiltonian is a tough thing because you're trying to make it in terms of an operator.
Wouldn't it be plus or minus?
Well, you know, how do you make an operator inside of a square root? And then when you square both sides, you can do it squared. And then remember, you get Maxwell's equations. And that leads to, so when you square the total energy on both sides, you get what's called, it's Maxwell's equation, but with a non-zero mass, it's called the Klein-Gordon equation. All right, but what happened is, the Klein-Gordon equation doesn't work for fermions, and only works for bosons. So what happened is Dirac forced this Hamiltonian to look something like this. C alpha matrix dot P plus beta matrix MC squared times psi equals IH partial psi with respect to T. So see, you can kind of imagine that this is like alpha or CP and then MC squared, and if you squared this, right, then you would get C squared P squared plus M0 squared C to the 4th, but then you have to get rid of the terms in the middle, all right? And so in order such that when you square this, so you get nothing in the middle, you just end up with C squared P squared, right, plus M0 squared C to the 4th, all right? That the only way that you can solve this is if, the only way to solve is if beta equals 1, 1, minus 1, minus 1, 3, 0, 1, 2, 1, 2, 1, 1, 2.